Hello there, and welcome to the Sleepless Astronaut channel. Tonight we're going to ask a question that has captivated humanity for as long as we've been able to look up at the night sky and wonder. A question so vast, so profound, that even beginning to answer it requires us to expand our minds beyond anything we experience in everyday life. A question that philosophers have pondered, that scientists have worked for centuries to answer, that still fills us with awe and wonder every time we truly contemplate it. Tonight, we're going to ask, how big is the universe? Not just big in the sense of being larger than a building or a city or a country. Not even big in the sense of being larger than Earth or the solar system, but truly, incomprehensibly, mind-bendingly big. Big in a way that challenges our very ability to conceive of size and distance and scale. Big enough that light itself, traveling faster than anything else that exists, faster than anything that can exist according to the laws of physics, takes billions upon billions of years to cross even a fraction of it. We're going to take a journey tonight, starting from exactly where you are right now, lying in your bed and expanding outward in stages. Step by step, scale by scale, we're going to zoom out from the familiar to the cosmic, from the human-sized world we understand intuitively to the vast reaches of space that extend far beyond anything our ancestors could have dreamed of, far beyond what most people ever take time to truly contemplate. And as we take this journey, as we contemplate the sheer immensity of existence, you're going to relax deeper and deeper into comfort. There's something profoundly peaceful about contemplating the universe's vastness, about realizing how small our daily concerns are in the grand scheme of things, about feeling connected to something so much larger than ourselves, so ancient and vast that it puts everything into perspective. So settle in wherever you are, get comfortable, adjust your pillow if you need to, pull your blanket a little closer, let your body sink into the surface beneath you, feeling fully supported, fully at rest. We're about to embark on the longest journey anyone could ever take, traveling from your bedroom to the very edge of everything. And we're going to take our time getting there. We're going to pause at each stage, letting the scale sink in, appreciating the distances before moving to the next level of magnitude. There's no rush. The universe isn't going anywhere. It's been here for nearly 14 billion years, and it will be here long after we're gone. Tonight we have all the time we need to explore it together. Let's begin where we are, right here, right now, with you lying in your bed, occupying a space perhaps 6 feet long and a couple of feet wide. This is a scale of human experience, the size of things we interact with every single day. Your body, the furniture in your room, the walls surrounding you, the ceiling above. These are the distances we understand intuitively, naturally, without effort, because we move through them constantly from the moment we wake until the moment we sleep. Your room extends perhaps 10 or 15 feet in each direction. You can walk across it in a few seconds. You can see from one wall to another with ease. This space is comprehensible, familiar, comfortable. It's the scale at which human life unfolds. Your home, your building extends a bit further, maybe a few dozen feet in each direction. Perhaps there are multiple floors, multiple rooms, but still it's a space you can navigate easily, a space that feels knowable and finite. You could walk through every part of it in a few minutes. Now expand outward to your neighborhood, your street, the few blocks surrounding your home. This extends perhaps a quarter mile. maybe half a mile. You could walk it in 10 or 15 minutes. You could see it all from a tall building or a hilltop. It's still a comprehensible scale, still something your mind can hold as a complete picture. Your town or city extends outward from here, covering perhaps a few miles or a few dozen miles depending on where you live. You can drive across it in minutes or perhaps an hour. You can see much of it from an airplane taking off or landing, watching the streets and buildings spread out below you in patterns of light and shadow. This is still a scale we can understand, still something we experience regularly. Now imagine rising higher, much higher, until you're looking down at Earth from space. From a few hundred miles up, the view changes dramatically. You can see the curve of the horizon, proof that Earth is a sphere. You can see the thin blue line of the atmosphere, a delicate shell of air surrounding the planet, protecting everything alive on the surface. You can see continents and oceans spreading out below you, weather systems swirling, clouds casting shadows, the Terminator line dividing day from night, moving slowly across the surface. This is the view astronauts have from the International Space Station, orbiting about 250 miles above Earth's surface. From here, entire countries are visible at once. You can see from coast to coast, from mountain range to mountain range. The scale has expanded dramatically. What took hours to cross by car can now be seen in a single glance. Earth's diameter is about 8,000 miles from pole to pole, slightly less than that at the equator because the planet bulges slightly at the middle due to its rotation. 8,000 miles. If you could somehow walk around the equator at a steady pace of 3 miles per hour, never stopping to rest or sleep or eat, it would take you about 2,700 hours to complete the journey. That's over 100 days of continuous walking, or more realistically, over a year if you walked 8 hours a day and rested the remainder. Earth is large by human standards, large enough that most people will never travel more than a tiny fraction of its surface in their lifetimes. The average person might visit a few countries, see a few different landscapes, but the vast majority of Earth remains unseen by any individual. There are forests and deserts and mountains and oceans that you will never witness firsthand, places that exist and have their own beauty and character, but are simply too far away, too numerous for one person to experience them all. But in cosmic terms, Earth is small, tiny, even, a marble hanging in the vastness of space. Let's expand our view and see just how small Earth really is when placed in its larger context. The Moon orbits Earth at an average distance of about 240,000 miles. That's about 30 Earth diameters away. If you could stack 30 Earths side by side, the Moon would be sitting just beyond the end of that stack. If Earth were shrunk down to the size of a basketball, about 9 inches across, the Moon would be a tennis ball about 2.5 inches across, sitting about 25 feet away. 240,000 miles is the farthest distance humans have ever traveled from Earth. Between 1969 and 1972, 12 astronauts walked on the Moon's surface, the only humans ever to set foot on another world. They traveled for 3 days each way, crossing the void between Earth and Moon in spacecraft smaller than a house, protected from the vacuum of space by thin shells of metal and plastic. No human has traveled beyond the Moon since 1972. The Moon remains the boundary of human exploration, the farthest we've ventured from home. Everything beyond it we've explored only with robotic probes and telescopes, sending machines to see what we cannot yet reach ourselves. 240,000 miles seems like an enormous distance, and by human standards it truly is. Light takes about 1.25 seconds to travel from Earth to the Moon. When Mission Control spoke to the Apollo astronauts, there was a noticeable delay in responses, a few seconds of silence, while radio signals traveled at light speed across the gap. But in the larger context of the solar system, the Earth-Moon system is tiny, intimate, a close pair orbiting together. The distances in the solar system are vastly larger than the space between Earth and its satellite. Let's zoom out further and see what surrounds us. The Sun sits at the center of our solar system, a massive ball of hydrogen and helium undergoing nuclear fusion, generating the light and heat that makes life possible on Earth. And Earth orbits this star at a distance of about 93 million miles. We call this distance one astronomical unit, abbreviated as O, and it serves as a useful measuring stick for distances within the solar system. 93 million miles. This is a distance so large that it becomes difficult to visualize or comprehend. If you could drive to the Sun in a car traveling at highway speeds, let's say 60 miles per hour, never stopping for any reason, it would take you about 175 years to arrive. Multiple human lifetimes spent driving through empty space. Light, traveling at its incredible speed, takes about 8 minutes and 20 seconds to cross this distance. When you see the Sun in the sky, you're seeing it not as it is right now, but as it was slightly over 8 minutes ago. If the Sun suddenly vanished, we wouldn't know for 8 minutes, because the light showing us the Sun is still traveling toward us. If we imagine Earth as a marble about half an inch across, then at the same scale, the Sun would be about 5.5 feet in diameter, roughly the height of a tall person. And this massive Sun would sit about 540 feet away from the marble Earth. That's about the length of 2 city blocks. This gives you some sense of the emptiness of the solar system. Even though the Sun is enormous and dominates the system with its gravity, it's separated from Earth by a vast gulf of empty space. But Earth is not alone in orbiting the Sun. There are other planets, each at their own distance, each following their own path through space. Let's visit them one by one and appreciate the growing distances. Venus orbits closer to the Sun than Earth does, at about 0.7 astronomical units, roughly 67 million miles from the Sun. Mercury, the innermost planet, orbits even closer, at about 0.4 astronomical units. These are the inner planets, close to the Sun, baked by intense heat and light. Mars, the red planet, orbits farther out than Earth, at about 1.5 astronomical units, roughly 140 million miles from the Sun. This is the farthest planet we've landed robotic probes on, the farthest world we've explored in any detail. The journey from Earth to Mars takes months when the planets are favorably aligned, and even radio signals traveling at light speed take between 4 and 24 minutes to cross the gap, depending on where Earth and Mars are in their respective orbits. Beyond Mars, the distances grow dramatically. There's a gap, a region filled with asteroids, rocky debris left over from the formation of the solar system. And beyond the asteroid belt, we encounter the giant planets, worlds so large that Earth would be lost in their shadows. Jupiter, the largest planet in the solar system, orbits at about 5.2 astronomical units from the Sun roughly 480 million miles. Jupiter is enormous, more massive than all the other planets combined. If Jupiter were hollow, you could fit over 1,000 Earths inside it. And it sits 5 times farther from the Sun than Earth does, taking nearly 12 Earth years to complete one orbit. At Jupiter's distance, sunlight takes about 43 minutes to arrive from the Sun. When you look at Jupiter through a telescope, you're seeing reflected sunlight that left the Sun nearly an hour ago, bounced off Jupiter's clouds, and traveled back toward Earth for another half hour or more, depending on where the planets are in their orbits. Saturn, famous for its beautiful ring system, orbits at about 9.5 astronomical units, nearly 900 million miles from the Sun. Saturn takes about 29 Earth years to complete one orbit. The planet appears smaller in our sky than Jupiter because it's almost twice as far away, though it's nearly as large physically. Uranus sits at about 19 astronomical units, roughly 1.8 billion miles from the Sun. This ice giant takes 84 years to orbit once. At this distance, the Sun appears much smaller in the sky, and sunlight is far weaker, providing only a fraction of the warmth and light that Earth receives. Neptune, the outermost planet, orbits at about 30 astronomical units, about 2.8 billion miles from the Sun. Neptune takes 165 years to complete one orbit. It has only completed one full orbit since its discovery in 1846. When you look at Neptune through a telescope, you're seeing reflected sunlight that left the Sun over 4 hours ago. These are immense distances, far larger than anything we experience in daily life. The outer solar system is so vast that even light, traveling at its incredible speed, takes hours to cross it. And yet we're still within the Sun's neighborhood, still in the region where planets orbit, still relatively close to home in cosmic terms. But the solar system doesn't end at Neptune. Far beyond the planets, there are other regions, other structures that extend much, much farther into space. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies, small worlds made of rock and frozen gases. Pluto orbits here, about 40 astronomical units from the Sun, along with thousands of other objects ranging from tiny chunks of ice to dwarf planets hundreds of miles across. The Kuiper Belt extends from about 30 astronomical units out to about 50 astronomical units, a vast donut of material surrounding the Sun. But even this isn't the edge of the solar system. Farther out, much farther, is the Oort cloud. The Oort cloud is a theoretical sphere of icy bodies surrounding the entire solar system. We've never directly observed it because the objects there are too small and too far away to see with our telescopes. But we infer its existence from the comets that occasionally fall inward toward the Sun, icy visitors from the outer reaches of the solar system. The Oort cloud is thought to extend from about 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun. At these distances, we need to shift our thinking from astronomical units to light years. 100,000 astronomical units is about 1.6 light years. A light year is the distance light travels in 1 year. Light moves fast, covering about 186,000 miles every second. In 1 year, light travels about 6 trillion miles. This is an almost incomprehensible distance. If you could drive at highway speeds without stopping, it would take you about 10 million years to cover 1 light year. The Oort cloud extends about halfway to the nearest star. It represents the outermost boundary of the Sun's gravitational influence, the edge of the region where the Sun's gravity is stronger than the gravity of other stars. This is the true edge of the solar system, and it extends far, far beyond the planets, into the darkness between stars. If you imagine the Sun as a grain of sand, a sphere about 1 millimeter across, then at this scale, Earth would orbit about 4 inches away. Neptune would be about 10 feet away, and the outer edge of the Oort cloud would be about 6 miles away. That's the scale of our solar system. A grain of sand with a few tiny specks orbiting relatively close by, surrounded by a vast sphere 6 miles across. Most of it empty, except for countless tiny chunks of ice too small to see. And in this model, where the solar system is 6 miles across, the nearest star would be another grain of sand sitting about 700 miles away. 700 miles of emptiness separating our sand-grained sun from the nearest other sand grain. This is the scale of interstellar space. The distances between stars are so vast that they dwarf everything within any individual solar system. The emptiness between stars is more profound than any emptiness we experience in daily life. Let's venture out into this void and see what we find. The nearest star to the Sun is called Proxima Centauri. It's part of a triple star system, Alpha Centauri, consisting of 3 stars orbiting each other. Proxima Centauri is the closest of the 3 to us, sitting at a distance of about 4.24 light years. 4.24 light years. That's about 25 trillion miles. Light takes 4 years, 2 months, and 27 days to travel from Proxima Centauri to us. When you look at this star in the night sky, assuming you're in the southern hemisphere where it's visible as a faint red point of light, you're seeing light that left the star over 4 years ago. You're looking into the past, witnessing the star not as it is in this moment, but as it was when that light began its journey across the void. If Proxima Centauri exploded right now, we wouldn't see the explosion for over 4 years. The light from the explosion would travel toward us at light speed, taking years to cross the gap. During those years, we'd continue seeing the star as it was, shining normally, with no indication of the catastrophe that had already occurred. 4 light years doesn't sound like much when you say it quickly. It's a small number, but the distance it represents is almost beyond human comprehension. If you could travel at 1,000,000 miles per hour, far faster than anything we've ever built, it would still take you 2,800 years to reach Proxima Centauri. Multiple human civilizations could rise and fall during the journey. With our current technology, the fastest spacecraft we've ever launched, Voyager 1, is moving at about 38,000 miles per hour relative to the Sun. At this speed, it would take about 75,000 years to reach Proxima Centauri. By the time the spacecraft arrived, it would be ancient, its electronics long dead, its mission forgotten, its builder's civilization transformed beyond recognition, or perhaps gone entirely. Proxima Centauri is the closest star, our nearest stellar neighbor, and it's effectively unreachable with any technology we can currently imagine. The distances between stars are simply too vast, the gulf of space too wide, the time required to cross it too long for any journey we can seriously contemplate with present-day technology. And Proxima Centauri is close by stellar standards. Most stars are much farther away. The stars you see when you look up at the night sky, those pinpoints of light scattered across the darkness, are at wildly different distances. Some are relatively nearby, a dozen or 2 dozen light years away. Others are hundreds of light years distant. A few are thousands of light years away, so far that their light has been traveling toward us since before recorded history, since before agriculture or writing or civilization. Sirius, the brightest star in our night sky, is about 8.6 light years away. Vega, a bright star visible in summer, is about 25 light years distant. Betelgeuse, the red supergiant star in Orion's shoulder, sits about 550 light years away. The light you see from Betelgeuse tonight left that star during the Renaissance, when Leonardo da Vinci was painting the Mona Lisa, when Columbus was sailing to the Americas. Each star is a sun, likely with its own system of planets, its own worlds orbiting in the darkness. And each is separated from us and from every other star by vast distances, by light years or tens of light years or hundreds of light years of empty space. Space is not crowded. It's overwhelmingly, almost inconceivably empty. If you imagine the galaxy as an ocean, each star is like a fish swimming alone in vast volumes of water, with the nearest other fish miles away. The space between stars contains almost nothing. No air, no water, barely even any stray atoms of hydrogen floating in the void. Just emptiness, darkness, silence extending for trillions and trillions of miles in every direction. And yet, despite this emptiness, there are so many stars that they collectively form structures, patterns, systems bound together by gravity. The sun and all the stars you can see in the night sky, all the stars that make up the familiar constellations, are part of a vast collection we call the Milky Way galaxy. The Milky Way is home to somewhere between 200 billion and 400 billion stars. The exact number is uncertain because we can't count them all, especially the faint ones hidden behind dust clouds or on the far side of the galaxy. But hundreds of billions is a reasonable estimate. More stars than there are grains of sand in a large bucket. More stars than you could count in 100 lifetimes of counting one per second without pause. And these stars are not scattered randomly. They're organized into a specific shape. The Milky Way is a spiral galaxy, a disk of stars with spiral arms curving outward from a bright central bulge. If you could somehow view our galaxy from outside, from a vantage point far above the disk, it would look like a pinwheel, a bright center surrounded by spiral arms studded with stars, glowing gas clouds where new stars are forming, and dark lanes of dust, obscuring the view deeper into the disk. Our solar system sits in one of these spiral arms, about halfway out from the center to the edge. We're in the suburbs of the galaxy, orbiting the galactic center at a distance of about 26,000 light years. The galaxy as a whole is enormous, about 100,000 light years in diameter from one edge to the other, and perhaps only 1,000 light years thick in most places, much thinner in proportion to its width than a CD or DVD. 100,000 light years across. Let that distance settle in your mind for a moment. Light traveling at its incredible speed takes 100,000 years to cross our galaxy from edge to edge. The light we see from stars on the far side of the Milky Way left those stars 100,000 years ago, at a time when modern humans were just beginning to spread across Africa and into other continents, when our ancestors were living in small groups, hunting and gathering, creating the first art and music and stories. The galaxy is so vast that even traveling at light speed, which is impossible for any object with mass, you could never explore more than a tiny fraction of it in a human lifetime. A journey across the galaxy at light speed would take longer than all of recorded human history, longer than agriculture has existed, longer than our species has been recognizably modern. And the numbers are staggering. Hundreds of billions of stars. If each star has even a few planets on average, there might be trillions of worlds in our galaxy alone. Trillions of places, each unique, each with its own characteristics, its own history. Rocky planets baked by nearby stars. Gas giants with dozens of moons. Ice worlds in the outer reaches of distant solar systems. Planets orbiting binary stars, seeing two suns in their skies. Planets in stable orbits that have remained unchanged for billions of years. Planets in chaotic systems where gravitational interactions make long-term stability impossible. Most of these worlds we will never see. They're too far away, too numerous, too scattered across the vast disk of the galaxy. Even if we could somehow travel at light speed, even if we devoted all of our civilization's resources to exploration, we could visit only a tiny fraction of them. The galaxy is simply too large, too full of worlds for any comprehensive exploration. And in all those trillions of worlds, how many have life? We don't know. Life might be common, arising on any planet with the right conditions. Or it might be rare, a lucky accident that happens only occasionally. We've found no evidence of life beyond Earth yet, but we've barely begun to look. The galaxy is vast, and we've examined only a handful of nearby stars in any detail. Somewhere out there, among the hundreds of billions of stars, there might be other worlds with oceans and atmospheres, forests and creatures, perhaps even intelligent civilizations looking up at their own night skies and wondering if they're alone. Or we might be the only life, the only consciousness, alone in a galaxy full of barren worlds. We simply don't know yet. But as vast as the Milky Way is, as incomprehensibly large as our galaxy seems, it's just one galaxy among countless others. Let's zoom out further and see our galaxy in its larger context, in the community of galaxies that surrounds us. The Milky Way is not alone in space. It has neighbors, other galaxies relatively nearby in cosmic terms. The nearest large galaxy is Andromeda, also called M31, a spiral galaxy similar in size and structure to our own. Andromeda sits about 2.5 million light-years away from us. 2.5 million light-years. This distance is so vast that even light-years, already incomprehensibly large, start to feel inadequate as a measuring unit. The light we see from Andromeda left that galaxy 2.5 million years ago, long before humans existed in anything like our current form, at a time when our distant ancestors were small, ape-like creatures in Africa, just beginning to use primitive stone tools. When you look up at Andromeda on a dark night, away from city lights, you can see it as a faint oval smudge in the sky, a dim patch of light that doesn't quite look like a star. That light has been traveling through empty space for millions of years to reach your eyes. You're seeing Andromeda not as it exists now, in this moment, but as it was in the distant past, millions of years before you were born, before your species existed, before your ancestors evolved. And Andromeda is moving. The galaxies are not static. They drift through space, pulled by gravity, and Andromeda is actually moving toward us. The Milky Way and Andromeda are on a collision course, falling toward each other, and in about 4 billion years they will merge, their stars and gas clouds mingling, their central black holes eventually combining to form a single larger galaxy. But this is so far in the future that it's barely worth contemplating. The sun will be nearing the end of its life by then, swelling into a red giant that will engulf the inner planets, including Earth. The Milky Way and Andromeda, along with about 50 smaller galaxies, form a structure called the local group. This is our immediate cosmic neighborhood, the cluster of galaxies bound together by gravity, orbiting their common center of mass. The local group extends about 10 million light-years across, with the Milky Way and Andromeda as the two largest members, and the other galaxies much smaller, dwarf galaxies containing only millions or billions of stars instead of hundreds of billions. 10 million light-years. At this scale, entire galaxies start to look small. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate about 20 feet away, with smaller galaxies like saucers and cups scattered in between, and the space between them is almost entirely empty. A few stray stars that have been ejected from their home galaxies wander alone through the intergalactic void, but mostly there's nothing, just emptiness extending for millions of light years. But the local group is just one small cluster among countless others spread throughout space. Let's continue zooming out and see the larger structures in the universe, the patterns that emerge when you look at distributions of galaxies on truly cosmic scales. Galaxies are not distributed randomly through space. They cluster together, bound by gravity into groups like the local group. And these groups cluster into larger structures called galaxy clusters and superclusters. The local group is part of a larger structure called the Virgo supercluster, which contains thousands of galaxies spread across about 100 million light-years. 100 million light-years. At this distance, our entire local group becomes a small point, one cluster among many in a larger structure. The Virgo cluster, near the center of the supercluster, contains over 1,000 galaxies packed relatively closely together. If you could somehow observe the Virgo cluster from a nearby vantage point, you'd see galaxies scattered like stars in our night sky, each one containing hundreds of billions of stars, each separated from its neighbors by millions of light years of empty space. But even the Virgo supercluster is just one structure among many. Recent observations using powerful telescopes and supercomputer simulations have revealed that superclusters are arranged in vast filaments and sheets, surrounding enormous voids where almost no galaxies exist. The universe at the largest scales looks like a cosmic web, with matter concentrated along filaments that surround empty bubbles hundreds of millions of light years across. This cosmic web structure formed through gravity over billions of years. In the early universe, matter was distributed almost uniformly, with only tiny variations in density from place to place. But gravity amplifies variations. Regions that were slightly denser than average attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to denser regions, becoming voids. Over billions of years, this process created the filaments and voids we see today, a network of structure that extends throughout the observable universe. We call the supercluster filament containing our local group the Laniakea supercluster. The name means immense heaven in Hawaiian, and it's appropriate. Laniakea contains about 100,000 galaxies spread across about 500 million light years. This is our address in the universe at the largest scale. We live in the Milky Way in the local group and the Virgo supercluster along the Laniakea filament. 500 million light years. Light takes 500 million years to cross this distance. The light we see from the far edge of Laniakea left those galaxies 500 million years ago, during the Cambrian period on Earth, when life was just beginning to diversify dramatically in the oceans, when the first fish were appearing, when arthropods were crawling along the seafloor, when plants had not yet colonized the land. And Laniakea is just one structure. There are similar filaments and superclusters throughout the observable universe, each containing thousands or tens of thousands of galaxies, each separated from the others by vast voids. The cosmic web extends as far as we can see in every direction, a pattern that seems to continue to the limits of observation, which brings us to the final scale, the ultimate zoom out, the largest structure we can observe, the observable universe itself. The observable universe is the region of space from which light has had time to reach us since the Big Bang, because the universe is about 13.8 billion years old, and because light travels at a finite speed, there's a horizon beyond which we cannot see. Light from more distant regions simply hasn't had time to reach us yet. No matter how powerful our telescopes become, no matter how long we wait, we will never be able to see beyond this horizon, because the light from those regions is still traveling toward us and won't arrive for billions more years. The radius of the observable universe is about 46 billion light years in all directions. This is larger than 13.8 billion light years, which you might expect for a universe that's 13.8 billion years old, because space itself has been expanding during the time that light has been traveling toward us. Galaxies have been moving away from us, not through space, but because space itself is stretching, carrying them along. This expansion means that galaxies which emitted light 13 billion years ago have now moved much farther away, and the most distant galaxies we can see are now about 46 billion light years away. The observable universe is a sphere about 92 billion light years in diameter, with Earth at the center, not because we're actually at the center of the universe, but because the observable universe is defined by what we can see from our location, and we can see equally far in all directions, which creates a sphere around us. Within this vast sphere, there are about 2 trillion galaxies, 2 trillion, each one containing hundreds of billions of stars, each star potentially hosting planets. The numbers become so large that they cease to have meaning in any intuitive sense. If you tried to count the stars in the observable universe, counting one per second without ever stopping, it would take you far longer than the current age of the universe. The stars outnumber the grains of sand on all the beaches on Earth. 2 trillion galaxies, each separated from the others by millions of light years of mostly empty space, arranged in filaments and sheets surrounding voids, creating a cosmic web that extends throughout the observable universe. And all of this, all 2 trillion galaxies, all the stars and planets and gas clouds and black holes and everything else, exists within a sphere 92 billion light years across. This is everything we can see, everything we can ever hope to observe. The observable universe contains all the light that has reached us, all the information we have about the cosmos beyond our immediate neighborhood. It's the sum total of what we can explore, at least in principle, even if we'll never have the technology to travel more than a tiny fraction of this distance. But here's the profound question that brings us to the edge of our journey and to the threshold of part 2. Is the observable universe all there is? Or does the universe extend beyond what we can see? Is there more space, more galaxies, more structure beyond our cosmic horizon? We'll explore that question in the next part of our journey. For now, rest here at the edge of the observable universe, looking out at the most distant galaxies we can detect, tiny points of light from the early universe, and contemplate what we've learned. We started in your bedroom, a space a few feet across. We expanded to your town, then Earth, then the moon's orbit. We traveled through the solar system, discovering distances measured in astronomical units. We ventured to the nearest stars light years away. We explored our galaxy, 100,000 light years across. We visited nearby galaxies millions of light years distant. We saw superclusters and cosmic filaments hundreds of millions of light years in extent. And finally, we reached the observable universe, 92 billion light years in diameter, containing 2 trillion galaxies. At each step, the previous scale became tiny by comparison. Earth became a speck in the solar system. The solar system became insignificant in the galaxy. The galaxy became one among billions. And all those billions of galaxies together occupy just the observable portion of a universe that might extend far beyond. The universe is vast beyond comprehension, so large that light takes billions of years to cross it, so large that most of it is forever beyond our reach, so large that even our galaxy, containing hundreds of billions of stars, is just one ordinary galaxy among trillions. And you are here on a small planet in one solar system, in one galaxy, in one small region of this vast cosmos, tiny by any objective measure. And yet, you're made of matter that has existed since the early universe, atoms forged in ancient stars, organized into a pattern complex enough to be conscious, to think and wonder and contemplate the immensity of existence. This is where we pause. We've reached the edge of the observable universe. But there's more to explore, more questions about what lies beyond, about whether the universe is infinite, about our place in this vast cosmic structure. Those questions await in the continuation of our journey. So here we are, having traveled from your bedroom to the edge of the observable universe, a journey of incomprehensible magnitude, crossing distances that light itself takes billions of years to traverse. We've seen Earth shrink from our entire world to a tiny speck, watched the solar system become insignificant in our galaxy, observed our galaxy become one among trillions scattered through space. And now we're looking outward at the most distant galaxies we can detect, galaxies so far away that their light has been traveling toward us since the early universe, since shortly after the Big Bang itself. But a profound question remains, a question that takes us even deeper into mystery, even further into the realm of the unknown and perhaps unknowable. Is what we can see all there is? Is the observable universe vast as it is the entire universe? Or is there more beyond our horizon, more space extending farther than light has had time to reach us? Perhaps infinitely farther. Let's think carefully about what the observable universe actually means. It's not a physical boundary, not a wall or edge where space ends. It's simply the limit of what we can see from Earth given the age of the universe and the finite speed of light. Light from galaxies beyond this horizon is still traveling toward us, but it hasn't arrived yet. In the future, billions of years from now, that light will reach Earth, assuming Earth still exists, and the observable universe will have expanded to include those previously invisible regions. But here's something strange that complicates this picture. The universe is expanding. Space itself is stretching, carrying galaxies apart. And the farther away a galaxy is, the faster it's receding from us. Not because the galaxy is moving through space, but because the space between us and that galaxy is expanding. At extreme distances, galaxies are receding faster than the speed of light. This doesn't violate Einstein's relativity because the galaxies themselves aren't moving through space faster than light. It's space itself that's expanding, and there's no limit to how fast space can stretch. The galaxies are just being carried along by the expansion. This means there's a boundary beyond which galaxies are receding so fast that their light will never reach us, no matter how long we wait. Even light that's emitted today from those galaxies traveling toward us at light speed is being swept backward by the expansion of space faster than it can make progress toward us. These regions are fundamentally, permanently beyond our observation. We can never see them, never receive information from them, never know what happens there. This boundary is called the cosmic event horizon, and it's currently about 16 billion light-years away. Galaxies beyond this distance are forever invisible to us. The observable universe is larger than this because we can see galaxies that are now beyond the event horizon, galaxies whose light was emitted billions of years ago when they were closer and able to send light that could reach us. But we're seeing those galaxies as they were in the distant past, and we'll never see what they look like today. So the universe we can observe is limited not just by the age of the universe and the speed of light, but also by the expansion of space itself. There are regions that will never be visible to us, not because they're too far away in principle, but because the expansion of space prevents light from those regions from ever reaching us. But those regions exist. Space doesn't end at our event horizon. Galaxies beyond our horizon are just as real as galaxies we can see. They have their own stars and planets and perhaps their own forms of life wandering about the universe. They're simply beyond our ability to observe them. How much universe is there beyond what we can see? Is it a little more just beyond our horizon? Or is it vastly more, extending far beyond the observable region? Or is it infinite, stretching on forever in all directions with no end? We don't know for certain, but we can make educated guesses based on observations of the observable universe. And those observations suggest something remarkable. The universe appears to be flat. What does flat mean in this context? It's a concept from geometry and Einstein's general relativity. Space can be curved in different ways. It can be positively curved, like the surface of a sphere, where parallel lines eventually converge. It can be negatively curved, like a saddle, where parallel lines diverge. Or it can be flat, like a plane, where parallel lines remain parallel forever. The universe's overall geometry determines its ultimate fate and whether it's finite or infinite. A positively curved universe would be finite, eventually closing back on itself like the surface of a sphere. If you traveled far enough in one direction, you'd eventually return to your starting point from the opposite direction. A negatively curved or flat universe could be infinite, extending forever with no boundary or edge. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, have measured the universe's curvature with remarkable precision. And the results show that the universe is flat, or at least very close to flat, within the limits of measurement error. If the universe is exactly flat, then it's almost certainly infinite. There's no edge, no boundary, no place where space ends. It extends forever in all directions. filled with galaxies and stars and structure similar to what we see in the observable universe. Beyond our horizon, there are more galaxies we'll never see. Beyond those, more still. And beyond those, more and more without end, extending infinitely far in every direction. An infinite universe is a strange concept to contemplate. It means there's no center, no special location. Every point in space looks roughly the same as every other point on large scales. Wherever you are, you'd see galaxies extending in all directions to your own cosmic horizon, and you'd appear to be at the center of your own observable universe. An infinite universe also has other strange implications. If space extends infinitely and is filled with matter, then given infinite space, every possible arrangement of matter must occur somewhere, no matter how improbable. There would be infinite copies of our observable universe scattered throughout the infinite expanse, each identical to ours in every detail. There would be infinite copies of you living identical lives, making identical choices. This seems absurd, but it's a logical consequence of infinite space filled with matter. In an infinite universe, anything that's possible, no matter how unlikely, must happen somewhere. In fact, it must happen infinitely many times. Of course, we can never verify this. Those duplicate regions would be vastly, incomprehensibly far away, far beyond our cosmic horizon, forever beyond observation. But they would exist if the universe is truly infinite. Not all scientists accept that the universe is infinite. Some think it might be finite but very large, much larger than the observable universe but not infinitely large. Perhaps the universe curves back on itself in some higher dimensional way we can't directly perceive, making it finite even though it has no edge or boundary in three-dimensional space. Imagine living on the surface of a sphere. The surface is finite, with a specific total area, but there's no edge, no boundary. You can travel in any direction and never reach an end. The surface curves back on itself in the third dimension. Perhaps our three-dimensional space curves similarly in a higher dimension, making the universe finite even though we can't perceive an edge. If this is true, the universe would be finite but still unimaginably large, probably much larger than the observable universe. We're unlikely to ever know its total size because we can only observe our local region, but it would have a specific finite volume. The question of whether the universe is finite or infinite remains one of the deepest mysteries in cosmology. We may never know the answer with certainty, but either way, whether finite or infinite, the universe is vastly larger than the region we can observe. Let's think about another profound question. Are we alone in all this vastness? With trillions of galaxies, each containing hundreds of billions of stars, most of which likely have planets, the sheer number of possible locations for life is staggering. Surely somewhere among those countless worlds, life must have arisen, just as it did on Earth. The question of whether we're alone in the universe has fascinated humanity for as long as we've been able to contemplate it. And the modern understanding of the universe's size makes it seem almost certain that we're not alone. The universe is simply too large, too full of possibilities for Earth to be the only place where life emerged. But we have no evidence of life beyond Earth yet. We've found no signals from alien civilizations. We've detected no biosignatures in the atmospheres of distant planets. We've seen no signs of megastructures or industrial activity on cosmic scales. The universe, as far as we can tell, is silent. This silence is puzzling. If life is common, if intelligence arises frequently, if technological civilizations are a natural outcome of evolution, then where is everyone? With billions of years for civilizations to arise and spread, some of them should be visible by now. The galaxy should be filled with signs of intelligence, but we see nothing. This puzzle is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" There are many proposed solutions. Perhaps life is rare, requiring an unlikely combination of conditions. Perhaps intelligent life is even rarer, with most life remaining simple and single-celled. Perhaps technological civilizations destroy themselves before they can spread to the stars, doomed by war or environmental collapse or some other catastrophe we can't yet imagine. Or perhaps the distances are simply too vast. Even if the galaxy is filled with civilizations, they might be separated by hundreds or thousands of light years, making communication nearly impossible. A signal sent between stars would take centuries or millennia to arrive, making any conversation absurdly slow. Perhaps intelligent species exist, but remain isolated on their homeworlds, unable to cross the vast gulfs between stars. Or perhaps we're looking in the wrong way, using the wrong methods, making assumptions about what alien civilizations would be like based on our own limited experience. Perhaps they communicate in ways we haven't thought of, or perhaps they're so different from us that we wouldn't recognize their signals even if we detected them. We don't know. The question of whether we're alone remains unanswered, but the search continues. We're building more powerful telescopes, developing better methods for detecting distant planets and analyzing their atmospheres, listening for signals from space with increasingly sensitive equipment. Perhaps someday we'll find evidence of life beyond Earth, or perhaps we'll conclude that we're truly alone, the only consciousness in a vast, empty universe. Either answer would be profound. Finding life elsewhere would answer one of humanity's oldest questions and open up entirely new areas of exploration and understanding. Finding that we're alone would be equally significant, suggesting that life and intelligence are rare and precious, that consciousness is a remarkable and fragile phenomenon that deserves to be protected and cherished. Let's shift our perspective now and think about time as well as space. We've been thinking about how big the universe is in spatial terms, but the universe also has a temporal dimension, a history that extends back billions of years. How old is the universe, and how does its age relate to its size? The universe is about 13.8 billion years old. This number comes from observations of the cosmic microwave background radiation, measurements of the expansion rate, and studies of the oldest stars and galaxies. The Big Bang occurred 13.8 billion years ago, and everything since then, all of cosmic history, has unfolded in that span of time. 13.8 billion years is an immense amount of time by human standards. All of recorded history, all of civilization, all of human existence is just a tiny fraction of cosmic history. Modern humans have existed for perhaps 300,000 years. Civilization has existed for perhaps 10,000 years. Written history covers only about 5,000 years. All of human experience, everything we've ever done or thought or created, has occurred in the last tiny sliver of cosmic time. If the history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, the Milky Way would form sometime in March. The solar system would form in early September. Life on Earth would appear in mid-September. Complex multicellular life would arise in mid-December. Dinosaurs would appear on December 26th and go extinct on December 30th. Modern humans would appear in the last few minutes before midnight on December 31st. All of recorded history would occur in the final few seconds of the year. We're latecomers to the cosmic story. The universe existed for billions of years before Earth formed, before our sun ignited, before our galaxy took its current shape. Stars were born and died, galaxies formed and collided. The universe evolved and changed, all before our little corner of space even existed. And the universe will continue long after we're gone. The sun will burn for another 5 billion years or so before exhausting its hydrogen and swelling into a red giant. The Milky Way will collide with Andromeda in about 4 billion years, merging to form a larger galaxy. Stars will continue to form from collapsing gas clouds for trillions of years, though the rate of formation will gradually decline as the available gas is used up or dispersed. Eventually, in the distant future, star formation will cease. The universe will enter an era dominated by existing stars, slowly burning through their remaining fuel. Red dwarfs, the smallest and longest-lived stars, will continue shining for tens of trillions of years. But eventually, even they will exhaust their fuel and fade. After the stars go out, the universe will enter the black hole era, dominated by black holes that persist long after stars have disappeared. Black holes evaporate through Hawking radiation, but the process is incredibly slow. A black hole the mass of the Sun would take 10 to the 67th years to evaporate completely. Supermassive black holes would take even longer, persisting for 10 to the 100 years or more. Eventually, even the black holes will evaporate. The universe will enter what's called the dark era, where all that remains are fundamental particles scattered through an ever-expanding space. The universe will be dark, cold, empty, with nothing remaining but dilute clouds of particles drifting apart forever. This is the ultimate fate of the universe if current understanding is correct. Not a dramatic ending, but a gradual fading, a slow dissolution into cold emptiness. The universe will expand forever, cooling forever, growing ever more dilute and dark until nothing remains but isolated particles separated by light years or more of empty space. It's a bleak picture in some ways, but it's also the natural conclusion of a universe that began hot and dense and has been expanding and cooling ever since. The Big Bang set everything in motion, and the expansion will continue indefinitely, carrying everything apart, dispersing all structure, until the universe reaches maximum entropy, and nothing interesting can happen anymore. But that fate is unimaginably far in the future, so distant that it's barely worth contemplating. For now, for the foreseeable future spanning trillions of years, the universe will remain a vibrant place filled with stars and galaxies and countless worlds. Let's return to our own place in this vast cosmos and think about what it all means. You're here on Earth, a small rocky planet orbiting an ordinary star in an unremarkable galaxy in one small region of the observable universe. By cosmic standards, you're tiny, occupying a few cubic feet in a universe that extends for billions of light years in every direction. Your life is brief. The average human lives perhaps 80 years if they're fortunate, less in many parts of the world. 80 years compared to the 13.8 billion year age of the universe. Your entire lifetime is a vanishingly small fraction of cosmic history, less than 1/1000th of the universe's current age. You exist for a brief moment in cosmic time, a flicker of consciousness in the vast expanse of eternity. And yet, you matter. Not because you're large or long-lived, but because you're aware. You can think, wonder, contemplate, understand. You're a part of the universe that has become conscious, that can look back at itself and marvel at its own existence. The atoms in your body were forged in stars billions of years ago. The hydrogen in your water was created in the Big Bang itself. The heavier elements, carbon and oxygen and nitrogen and iron and all the rest, were created in stellar cores and supernova explosions, then scattered into space to eventually become part of new stars, new planets, and eventually you. You're made of ancient material, recycled through multiple generations of stars, part of the great cosmic cycle of birth and death and rebirth. Every atom in your body has a history stretching back billions of years, a journey through the cosmos that eventually led to you. And you're connected to everything else. The earth beneath you is made of the same stardust. The air you breathe is made of atoms from ancient supernovas. The sun that warms you is fusing hydrogen into helium, the same process that powers stars throughout the universe. You're not separate from the cosmos. You're part of it, woven into it, made of the same substance, following the same laws of physics, participating in the same grand story of cosmic evolution. There's something profound and humbling about this realization. All your concerns, all your worries, all the things that occupy your mind day to day, they're real and valid and important to you. But in cosmic context, they're small. The universe is vast and ancient and will continue long after you're gone. Your problems, whatever they are temporary and local, significant to you but not to the cosmos. And there's something comforting in that perspective. When you feel overwhelmed, when life seems too difficult, when you're stressed or anxious or afraid, you can step back and remember how small you are, how brief your life is, how vast and ancient and indifferent the universe is. Your problems are real, but they're also small and temporary in the grand scheme of things. The universe will continue regardless of what happens to you, and somehow that makes it easier to bear. But there's another side to this perspective. If you're small and brief and insignificant in cosmic terms, then so is everyone else. We're all in this together, all tiny sparks of consciousness in a vast, dark universe, all sharing this small planet, all made of the same ancient stardust. The things that divide us, the conflicts and disagreements and hatreds that seem so important, they're even smaller in cosmic context than individual lives. From the perspective of the universe, we're all the same. We're all humans on Earth sharing this one small world, this tiny island of life in the vast cosmic ocean. The boundaries we draw, the differences we emphasize, the reasons we find to fight and hate each other, they're all human constructs, all temporary and arbitrary and ultimately meaningless when viewed from the cosmic perspective. Perhaps if more people could truly grasp the scale of the universe, truly understand how vast and old and indifferent it is, how small and brief and fragile we are, we might treat each other better. We might recognize that we're all in this together, all sharing one small planet in an incomprehensibly large universe, and that we should take care of each other and our world because it's the only one we have. This is the overview effect, the shift in perspective that astronauts report after seeing Earth from space. When you see our planet as a small blue marble hanging in the blackness, with no visible borders, no obvious divisions, just one unified whole, it changes how you think about humanity and our place in the universe. The things that seemed important on the ground, the national boundaries and political divisions and ethnic distinctions, they all fade into insignificance. What remains is the realization that we're all humans on one small world, and we need to work together to preserve it. Now imagine taking that perspective further. Imagine seeing not just Earth from space, but the solar system from interstellar distance. Our sun is just another star among billions. Imagine seeing the Milky Way from outside, a spiral of stars in which our solar system is one tiny, insignificant point. Imagine seeing the observable universe from some impossible vantage point, 2 trillion galaxies scattered through space, each containing billions of stars, each star potentially hosting worlds. From that perspective, Earth is not just small, it's invisible. Our entire planet, everything we've ever done or thought or created, all of human history and civilization and struggle, all of it occurs on one invisible speck in an ocean of space so vast that it defies comprehension. We're smaller than small, briefer than brief, more fragile than we can possibly imagine. And yet, we're here, we exist, we're conscious. We can think about all of this, understand it, marvel at it. We're the universe's way of knowing itself, of understanding itself, of appreciating its own vastness and beauty and mystery. That's something remarkable, something worth celebrating, even if we're small and brief and ultimately insignificant in cosmic terms. Let's think about the universe's beauty for a moment. We've been talking about size and scale and distances, focusing on the measurements and numbers. But the universe is also beautiful in ways that transcend mere size. The spiral arms of galaxies, glowing with newly formed stars. Nebulae, vast clouds of gas and dust lit by the radiation of hot young stars, creating colors and shapes that seem almost artistic. Planetary nebulae, shells of gas expelled by dying stars, creating perfect rings and spheres in space. Supernova remnants, expanding shells of debris from stellar explosions, creating intricate filaments and structures. The aurora on Earth, shimmering curtains of light in the polar skies, created by charged particles from the sun interacting with our magnetic field. The aurora on Jupiter, far more intense, creating permanent glowing rings around the poles. The rings of Saturn, countless particles of ice reflecting sunlight, creating one of the most beautiful sights in the solar system. Galaxies colliding, their forms distorted by tidal forces, creating bridges of stars between them. Galaxy clusters, hundreds or thousands of galaxies bound together by gravity, creating dense fields of light against the darkness. The cosmic web, filaments of galaxies extending across billions of light years, surrounding vast empty voids, creating structure at the largest scales. The universe is not just vast, it's also beautiful, filled with structures and phenomena that inspire awe and wonder. From the smallest scales to the largest, from the most familiar objects in our night sky to the most distant galaxies at the edge of observation, the universe rewards those who take time to observe it, study it, contemplate it. And beauty is not the universe's only remarkable feature. The universe is also comprehensible. The fact that we can understand it at all, that the laws of physics are consistent and mathematical and discoverable, that the universe follows rules we can learn and use to make predictions, This is remarkable in itself. The universe could have been chaotic, random, impossible to understand, but it's not. It follows consistent laws. Gravity works the same way here as it does in distant galaxies. Light behaves the same way throughout space and time. The fundamental constants of nature seem to be truly constant, the same everywhere we look. This consistency allows us to understand the universe, to build telescopes and spacecraft, to explore and discover and learn. We're fortunate to live in a universe that's comprehensible, that reveals its secrets to those who ask the right questions and make the right observations. We're fortunate to live in a time when we have the technology to explore the universe, to see distant galaxies, to detect gravitational waves, to find planets around other stars. Previous generations could only wonder about these things. We can observe them, measure them, understand them, and future generations will understand even more. The exploration of the universe has barely begun. We've observed only a tiny fraction of the planets in our galaxy. We've barely begun to search for signs of life beyond Earth. We've detected only a few gravitational wave events. We've observed the universe at only a few wavelengths of light and a few other types of radiation. There's so much more to discover, so many questions still unanswered, so many mysteries waiting to be solved. The universe is vast, yes, but it's also knowable. Not completely, not entirely, but enough that we can understand our place in it, appreciate its size and age and structure, marvel at its beauty and complexity. We're small, but we're not insignificant. We're brief, but we're not meaningless. We're part of something vast and ancient and wonderful, and that's something to celebrate. Let's bring our journey to a close now. We've traveled from your bedroom to the edge of the observable universe and beyond, contemplating what might lie past our cosmic horizon. We've thought about whether the universe is infinite or finite, whether we're alone or accompanied by countless other civilizations scattered among the stars. We've reflected on our place in this vast cosmos, our significance despite our tiny size, our connection to everything through the atoms we're made of, and the laws of physics we obey. The universe is incomprehensibly big, 92 billion light years across in the observable region, possibly infinite beyond that, containing 2 trillion galaxies, each with hundreds of billions of stars, each star potentially hosting worlds, filled with structure and beauty and mystery at every scale from the smallest to the largest. And you're part of it. A small part, a brief part, but a part nonetheless, made of stardust, animated by the same physics that governs stars and galaxies, conscious and aware and capable of understanding your place in the cosmic story. Tomorrow the sun will rise over your small part of Earth. Your day will begin, filled with the tasks and concerns and joys that make up human life. And the universe will continue vast and ancient and indifferent, unaware of you, but containing you nonetheless. But tonight, rest here with this cosmic perspective. Let the vastness wash over you, not overwhelming but comforting. The universe is big and you are small, and that's okay. You're exactly where you should be, part of something so much larger than yourself, connected to everything through billions of years of cosmic history. Sleep now. Let your mind settle. Let your thoughts fade. The universe will continue without your awareness. Stars will shine. Galaxies will drift through space. The cosmos will evolve according to its ancient laws. And you'll rest here on your small planet, safe and peaceful, part of it all. The universe is vast, but you're here. And that's enough. Good night, cosmic traveler. Rest well. Dream of stars and galaxies, of the incomprehensible vastness of your place in it all. Or dream of nothing. Just sleep deeply and peacefully. The universe holds you gently in its vast expanse. You're home. You've always been home. And the cosmos that made you watches over you as you sleep. Good night. Our story ends here. If you're still awake and would like to stay with us in future content, don't forget to subscribe to the channel. And if it's already late, I simply wish you a peaceful night's sleep. The brown noise you're about to hear is a low-frequency, steady sound designed to help calm your mind and relax you as you sleep. Good night.